This video covers section 5.1, which is the introduction to probability. So probability is a number between 0 and 1 that describes the proportion of times the outcomes of a random process would occur in a very long series of trials. So the law of large numbers says that if we observe more and more trials of any random process, then the proportion of times a specific outcome occurs will approach the true probability of that outcome. So know that probabilities are unpredictable in the short run, but they become more predictable in the long run. So that's the idea of the law of large numbers. Okay, so remember again that probability is the number between 0 and 1. So that means essentially that it's a percentage. So in this first example, we're going to look at that law of large numbers. So a teacher claims that there's a 50% chance that she will collect homework for a grade on any given day. 1 week, she collected all 5 daily homework assignments. A student in the class was upset and explains that the teacher should not collect homework assignments the following week in order to honor her 50% probability claim. Okay, so that would mean that week she selected all of them, the next week she selected none, and so that would average out to 50%. Is the student's reasoning correct? So the idea of this is that they're unpredictable in the short run. So this meets that standard that she can do whatever she wants, but for the scope of the whole year, it should end up being 50% because they're predictable in the long run. So that means that the student's reasoning is not correct based on the law of large numbers. So it's not going to be a yes because it's unpredictable in the short run. So a week is a short run. So no, if the teacher collects homework 5 days in a row, it's not possible for the probability of homework being collected to be 0.5. That is not true. So no, collecting homework and not collecting homework are equally likely in the long run. So whether or not the teacher collects homework on any single day cannot be determined. And that demonstrates the law of large numbers. So ultimately, if what you expect to happen doesn't, it doesn't mean it won't after many, 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 many more trials. So just kind of a reminder about some rules with probability. Remember that if the probability is 0, that means whatever that event is never happens. If it's 1, it means it always happens. So they used an example of rolling a 7 on a die. Will never happen because the die only has numbers 1 through 6, versus rolling a 1, 2, 3, 4, 5, or 6 will always happen because those are the only numbers that are on the face of a die. And then for 0.5, that means it's going to happen half the time in the long run, remember, is the rule. And so that would mean, like, the example I think they gave was rolling an even number because half of the digits on a die are even numbers. And then just a reminder that when they talk about a fair coin, it means that all outcomes are equally likely regardless of what happens before that. So meaning that if I flip 20 heads, I still have a 50% chance of flipping tails on the next turn. That the previous flips have no influence on what happens next. So previous flips have no influence on the next one. Okay, so we're gonna look at an example and kind of talk about a type of graph. So using a long run relative frequency graph. So you can use a long run relative frequency graph to conclude about an outcome by reading the typical Y value on the right-hand side. So what's happening here is that this represents the number of samples, is our x-axis. And this is that probability. And so the graph below shows the relative frequency of tossing a coin and observing heads after 30 trials. As the number of trials increases, the relative frequency fluctuates less and less and gets closer to the theoretical probability of 0.5. So notice that it's our first flip, right? it's 100% because we only flipped it one time. So it was heads, and so it was a 1. And then we must have gotten a tails because it's right on 50, the second flip, right? So heads and a tails makes 50%. Then it must have gotten another tails, oh, maybe a heads because it increased, a tails, a heads, a heads, a heads, tails, heads, tails. So it's evening out. And so remember that this is that theoretical probability of 0.5. So that's the true probability of flipping a coin. And so what's happening is that this is showing us that it's close to 0.5. It actually ends up, if I think about where the middle of this is, it's about 43%, which is close to the true mean. So 43% of the time in 30 trials, they got heads. Okay, so what would happen here is that adding more trials will bring that value of 43%, the probability of 43% to 50%. Okay, so the more and more and more samples and trials that we do, the higher it will get closer and closer to 50%. Sorry, I wrote samples here, but this should have said trials, and I got distracted. Okay, so a simulation simulates a random process, imitates a random process in such a way that the simulated outcomes are consistent with the real world outcomes. So there are 3 steps to create a simulation. The first step is to describe a random process. So whatever you're doing should match the probability claimed in the problem. So if there's 2 possible outcomes, you should flip a coin. If there's 6 possible outcomes, you should roll a die. Really, the easy way is using a table of random digits and a random number generator and assigning the first however many numbers to one outcome and then the rest to another, where the total number of outcomes matches your probability or the sample that you took. And then you perform many trials. So the idea is that you're doing this many times so you can get a better long run relative frequency graph so that you can better match what that probability actually is for the population. And then you're going to use that result to answer a question of interest. So we've got 2 examples down here, maybe 3. A manufacturer of baseball hats claims that approximately 30% of people regularly wear baseball hats. From a random sample of 20 students at your school, you find that only 4 wear baseball hats regularly. This gives you reason to believe that the manufacturer's claim of 30% is too high. So let the digits 0 to 2 represent wearing a baseball hat, and the digits 3 to 9 represent not wearing a baseball hat. Use the table of random numbers to run one trial of this simulation. So their claim was 30%, right? So if I think about 30%, that means 3 out of 10, okay? And so notice that they're picking digits 0 to 2 because there are 3 of them, and then going all the way to 9 because from 0 to 9, that's 10 numbers, okay? So that's where they're getting these values from. And so they're matching the manufacturer's claim there. And then what we're gonna look at ultimately for determining if something was true or not is we would look at our results and compare that to see if it's statistically significant. And so these are single digit numbers. So we're gonna do one trial of the simulation, which means that we're picking 20 students, right? So we had a sample of 20 students, so we're simulating that sample. Okay, so I'm looking for the first 20 numbers, and that's going to give me my sample. So since these are 5 numbers in each box, that means I'm really just going to look at the first 4 boxes. That's going to be my sample. So what I'm thinking about then is the number 0 to 2, that means they're going to wear a hat. So I have 1, 2, 3, 4, only 5 people wearing hats. The rest are not wearing hats. So that means that my whole first group is not wearing a hat. So those are all N's. So whether it's N, 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 N. So if I look at my options, that means that my answer should be A. So let's double check. So then hat, hat, 3 no's, right? This one is, only this one is an H. This one is, the middle 2 are H's. So that means that the correct sequence of outcomes for that simulation would be the answer for A. For B, the next problem, we're going to look at drawing a conclusion from information about simulation. So a study reported that about half of high school seniors study for upcoming math tests. So that's their claim, right? So the claim is a 50%. To find out if this applies to seniors at Garfield High School, a simple random sample of 30 seniors was asked if they study for their math tests. If this was true, right, if 50% was true, that would mean that 15 seniors said that they studied. However, they got 19. Okay, so out of 30 seniors, they got 19. A dot plot is provided to show the results of 40 trials of this simulation. So we've got the data from 40 trials. Does this provide convincing evidence that the seniors at Garfield High School study more than the report stated? So the report stated that this should be the mean value, right? So that the probability should be at 15. However, at Garfield, they said 19. Okay. So if I look at how many items I have here, so this was out of 40 trials. So there's only 1 out of the 40 trials that provided something that was greater than 19. Okay, and again, I picked greater because my the claim was below that number. So I want to see if it's statistically significant to get higher than that number. So if I divide 1 by 40, that's 2.5%, which is less than 5%. So that means that this is statistically significant. Okay, so again, once I found that 19, I want to go the opposite direction of where their claim was to see if it's statistically significant. So if that number is less than 5%. So 1 out of 40 trials, which is 2.5%, is less than 5%. So that means that yes, Garfield High School study is more than the report stated. Okay, so I'm always comparing it to that. I'm not looking at the data, right? It is true that more than half of the simulated results are over 15, but it always has to do with that statistical significance. So you're looking at what their claim was, that it was 19, and that's bigger than the reported percentage. And so you want to go to the bigger side and figure out if that percentage is 5% or lower. In the last one, we've got a fitness expert that claims that 25% of adults do not know how to swim. To test this claim, a simple random sample of 20 adults is taken. 2 of the adults do not know how to swim. So they've got the claim is 25%, which out of 20 would be 5 out of 20, right? So 5 out of 20 would be their claim. They take a sample and it's 2 out of the 20 don't know how to swim, so that's here. A simulation of 100 trials is conducted based on the assumption that 25% is the true probability that an adult does not know how to swim. Based on the dot plot of the simulation results of the sample of 20 adults, which conclusion can be made? So if I look at this, I want to count how many dots are here less than that 2 out of 20 to see if that's statistically significant. So I've got 3, 6, 9, 12. So it looks like here I've got 12 out of, we had 100 trials. And so that's 12%. Okay, so 12% of the trials gave a result of 2 or fewer. So 12% is not less than 5%. So that's not statistically significant. So that means that we cannot, that's not unusual, okay? So if I'm looking at this, the actual probability an adult cannot swim is only 12%. So that's not true. That's not what that 12% means. It's clear that exactly 5 out of 20 adults will be non-swimmers. That's not clear. If we continue to take more samples of 10 adults, the center of the distribution would shift to 2. We didn't take 10 samples of 10 adults, so that's definitely not true. However, there is about a 12% chance of 2 or fewer non-swimmers in a group of 20. That is not unusual and is not convincing evidence that the true probability that an adult cannot swim is less than 25%. Okay, so remember that when I calculate that percentage, I'm looking at whether that's unusual, aka statistically significant, by being less than 5%.